Hello everyone, welcome to Tuteetute. In this video, we will see the concept of perpendicular polarization. So in case of oblique incidence, already we have seen how the electromagnetic wave incident on the interface. So interface is generally the boundary which is separating the two media. That part already we know. And in this analysis, we have to take a normal to the incidence. Okay, that means normal to the boundary or the interface we have to consider. And from one medium to other medium, the electromagnetic wave is traveling. Whenever it is incident on the boundary which is separating the two media, okay, so what will happen means because of the impedance mismatch, some part of the signal will be reflected back into the same media and remaining part will be entering into the medium 2. So we have to study about this particular reflecting wave and a transmitted wave. Okay, and in that particular case we have two types. One is perpendicular polarization and second one is parallel polarization that we will see in the next video. Okay, now in detail we will study about the perpendicular polarization. So before going to see the definition of the perpendicular polarization, just we will establish the situation here. So you see here, we will consider this is z-axis, okay, and this is x-axis, and here y-axis is coming out of the boundary, okay, that means out of the screen. That is what I want to say. So x-axis is this one, y-axis is this one. That means whatever you are seeing here, this is the xy plane. Okay, this plane has been created because of the changes in x and changes in y. So this is the boundary actually. So you should not see the line, you should see the plane which is separating first media and second medium. Okay, so left side to us here, what is there? Medium 1. And right side to this particular plane, xy plane, what is there? Medium 2. I am saying it is medium 1, it is medium 2. That means those two are two different medium. Okay, so how to categorize these two media means by using their impedances. So medium 1 is having the impedance is eta 1, medium 2 is having the impedance is eta 2. Okay, so these two are the impedances, eta 1, eta 2. Since these two are different, that's why these two are different media. Okay, for the same medium, we will be having the same impedance. Okay, throughout the material, we will consider that is having the same impedance because we will assume that is a homogeneous medium. So here we have taken two different media and those two are separated by this xy plane boundary. That is what we can able to assume here. And we can able to say here, because here the impedance is eta 1 and the impedance is equal to root of mu by epsilon. So it is having the permeability mu 1 and permittivity epsilon 1 and conductivity sigma 1. Like that we can able to characterize this particular medium 1. Similarly, the medium 2 is having the permeability mu 2, permittivity epsilon 2 and conductivity sigma 2. Okay, because these values are different, that's why these two are different media. Okay, because it is having mu 1, epsilon 1, sigma 1, here eta 1 is the impedance we have, and here mu 2, epsilon 2, sigma 2 are available. That's why here we have eta 2. Generally, this impedance formula is given like this, na? Square root of j omega mu by sigma plus j omega epsilon. So here you can able to see it depends on mu, epsilon, sigma. So that we have given like this. Okay. So whenever impedance mismatch is there, that means these two impedances are different. So at this boundary, whenever the wave is traveling from medium 1 to medium 2, whenever this incident electromagnetic wave is touching this particular boundary, that is the xy plane which is separating the two media, immediately it will be affected by the impedance eta 2. Okay, up to that particular time it is traveling in the medium having the impedance is equal to eta 1, but suddenly what is happening? The wave is seeing the different impedance here, that is eta 2. So this is called impedance mismatch. Whenever impedance mismatch is there, we can able to tell that reflection will be possible. Okay, from the transmission line theory also we can able to tell that one. Whenever the load impedance and the characteristic impedances are different, then what will happen? Reflections are possible towards the source. So here also same thing. The wave is traveling in the medium 1. Suddenly it is seeing the different impedance, so that some part of the wave will be reflected back. That is called reflected wave. And the remaining part will be sending into this particular medium 2, that is called transmitted wave. So here we are going to deal with 3 electromagnetic waves. One electromagnetic wave we have incident, okay, and it is traveling here in the medium 1 having the impedance is eta 1. Whenever it is touching this particular boundary, and immediately it is seeing the different impedance, that is eta 2, and because of this impedance mismatch, some part of the wave or some power of the wave will be reflected back into the same medium, and remaining will be transmitted into the medium 2. So this is called incident electromagnetic wave, this is the reflected electromagnetic wave, and it is the transmitted electromagnetic wave. Okay, these things already we have seen in case of the normal incidence, but particularly in case of the oblique incidence, we are going to work with the perpendicular polarization and parallel polarization. So what is about that one we are going to see in detail now. Okay, so now anyhow we are going to deal with this oblique incidence only. So what is the meaning of oblique incidence? What is the meaning of the oblique incidence means? This is the boundary I have mentioned, that is XY plane, and normal to the boundary. Okay, that is also required for us. So what is normal to the boundary? It is XY plane means surely we can tell Z axis is normal to XY plane. So that's why here we have mentioned that is the Z axis, and it is a normal to the boundary, normal to the interface. Okay, or normal to the XY plane. So this is the normal. Okay, this is the normal we can tell. So in the medium 1 we have to incident one particular electromagnetic wave. So now I am taking like this. Just I have redrawn the boundary here. X, this is X axis, Y axis is coming towards you, and this is the normal. Okay, now the electromagnetic wave is incident on this particular boundary like this. Okay, so electromagnetic wave is traveling in the medium 1, coming and striking this particular boundary at this particular origin, we can able to say. Okay, then because of the impedance mismatch, as I said earlier, some part of the wave is reflected back and remaining part will be transmitted into the medium 2. Like this we have taken. And here, in order to talk about what are the angles related to the normal, those things also we have to take. Those angles are like this. The incident wave is making the angle theta I with the normal to the interface, that is angle of incidence. Okay, this theta I is said to be angle of incidence. Angle of incidence related to incident wave, angle of reflection is related to reflected wave, angle of transmission is related to this transmitted wave. This is a transmitted wave into the second medium. So all these angles are with respect to normal, not with respect to the interface, not with respect to the boundary. Okay, the wave vector, whatever the wave vector is there of the incident wave or the reflected wave or the transmitted wave, this wave vector is making the angles with respect to normal to the boundary we have to consider. This is the boundary, but this is the normal. So this incident wave vector is making angle theta I with the normal. This is a reflected wave. This reflected wave is making the angle theta r, angle of reflection, theta r with the normal to the boundary. And this particular transmitted wave is also making the angle with respect to this normal to the boundary, that is theta t, angle of transmission. You should not take angle like this. This is not theta t. This is the theta t. Angles should be with respect to normal to the boundary, normal to the interface. That is one of the important point you need to remember. Okay. Then, now the question is, why do we have only two types of the polarizations in this particular oblique incidence case? One is perpendicular polarization, second one is parallel polarization. Why? Why means a very simple thing. You see, here right hand coordinate system we have to use, and the electromagnetic wave having electric field, magnetic field and direction of propagation. These three are perpendicular to each other. Already we know about that one. Okay. So here, in order to apply this particular concept, we are using this right hand thumb. right hand rule we are applying. Okay, right hand thumb is representing, for example, it is the direction of propagation. Okay, then this thumb is representing electric field orientation. This particular middle finger is representing the magnetic field orientation. So you see, this is the direction of propagation already we have mentioned. That means our thumb should indicate like this. Okay, these three are perpendicular only, na? That means this is the direction of propagation, electric field and magnetic field. These three are perpendicular to each other always, because we are working with a transverse electromagnetic wave. So I have kept like this. But there is no rule. Even this particular thumb is representing the direction of propagation in this way. I no need to keep this middle finger, that means electric field orientation and magnetic field orientation like this only. Okay, you see carefully, I can orient like this also. Now also we are following the same rule. Thumb is always in the direction of propagation only, and this thumb is perpendicular to this forefinger and middle finger. That means direction of propagation is perpendicular to this particular electric field orientation and magnetic field orientation. I no need to keep like this also. I can keep like this also. I can keep like this also. I can keep like this also. In any orientation, we can able to take this electric field and magnetic field orientations in such a way that this thumb is available in the direction of propagation. Okay, so we can take like this. In any direction we can able to take. The orientations of the electric field and magnetic field can be taken in any direction in such a way that we are following the two rules. One is thumb is in the direction of propagation only, and these three are perpendicular to each other. Then why we are studying only two things only? Actually, if I keep like this, this is called parallel polarization, because you see this particular screen. For the screen, the electric field is parallel now. Okay, for the screen, the electric field is parallel. Electric field is nothing but this forefinger. So because it is parallel to the screen, we can able to tell it is a parallel polarization. Instead of this one, you can take like this also. Okay, now you can see thumb is in the direction of propagation only, and this forefinger is available perpendicular to the screen. That's why it is called perpendicular polarization. What about this one? What about this one? What about this one? Okay, here why we are studying only parallel polarization, where electric field is parallel to the screen, and why we are studying only perpendicular polarization, where the electric field is perpendicular to the screen. What about the remaining directions? What about the remaining directions? Why do we have only two topics in case of the oblique incidence? Why? Why means, you see, this is one thing, parallel polarization, this is the perpendicular polarization. If the wave is like this, then this electric field can be resolved into two components. One is parallel and second one is perpendicular. If the wave is not available like parallel polarized electric field orientation and perpendicular polarized electric field orientation, then that particular thing can be resolved into these two only. Whatever the orientation of the electric field, whatever the orientation of the magnetic field, we can resolve those fields into two fields. One is parallel polarized field, second one is the perpendicular polarized field. Okay, to understand that one, for example, this is the electric field. We can resolve this one into two vectors. One is parallel, second one is perpendicular. If the electric field is like this, okay, this can also be taken, or this can also be resolved into two vectors. One is parallel, second one is perpendicular. If it is like this also, that is possible. So any orientation, okay, that can be taken only two things. Na? One is parallel polarized wave, second one is the perpendicular polarized wave. That's why we are studying only two. Okay, that is the introduction about the perpendicular polarization. But whatever the definitions I have given for the parallel polarization and perpendicular polarization, those things not with respect to the screen, we will give the with respect to plane of incidence. So what is plane of incidence? One by one we'll see. So now we'll see exactly what is this perpendicular polarization. Now interface. Already you have understood what is the interface or what is the boundary which is separating the two media. Okay. So in our example, what is interface here? XY plane. XY plane is the interface, or this can also be called as boundary, which is separating the two media actually. Okay. Next, normal to the interface. Okay, already I have given the importance to the normal to the interface, because with respect to normal only we are defining theta I, theta R and theta T. So normal to the interface is here because it is XY plane. Normal to the interface is Z axis in our case, Z axis. Since I have taken XY plane is the interface, here Z axis is the normal. No need to consider always XY plane only. Okay. Then plane of incidence. Plane of incidence means, now you see carefully, the plane which contains incident electric field, okay, or incident wave and normal. These two must be available on the plane. That plane is called plane of incidence. So the plane of incidence is the plane contains wave, incident wave actually, okay, incident wave and normal. Okay, these two must be there on a single plane so that we can able to tell that is the plane of incidence. Now in our case, what is the plane of incidence? You see here, this screen you observe. Okay, whatever the screen you are seeing, that screen contains the wave, the electromagnetic wave and the normal also. Okay, or you see in which plane this normal to the boundary, normal and electromagnetic wave, these two are available. This boundary only, this plane only na. Okay, what is that plane? XZ plane. Okay, XZ plane, in our case, XZ plane is the plane which contains normal to the boundary and incident wave. So that here this plane of incidence is XZ plane. XZ plane. That is what I want to tell. Okay, now we will define what is Snell's law. Snell's law having two things. Snell's law of reflection, Snell's law of refraction. Two things are there. Snell's law of reflection is simply the relation between incident angle and a reflected angle. Okay, or angle of reflection and angle of incidence. So theta I, theta R relation is given by Snell's law of reflection, that is theta I is equal to theta R. Very simple thing. Okay, theta I is equal to theta R. This is the Snell's law of reflection. That means always you can able to remember one thing, that is whatever the angle of incidence is there, same angle will be there for the angle of reflection also. Okay, now this angle of this Snell's law of refraction will give the relation between angle of incidence and angle of transmission. That means theta I and theta T. The relation between these two will be given by this is Snell's law of refraction. That one I am writing here. That is N1 sin theta I is equal to N2 sin theta T. This is the Snell's law of refraction. You see, theta I, theta T are related by using this particular equation. And one important point I am telling, this N1, N2 are not impedances of the media. Here we have represented the impedance of the media with eta 1, eta 2. This is the letter eta 1, this is the letter eta 2, not N1 and N2 here. Impedances are represented with the eta 1, eta 2, and here this N1, N2 are the refractive indices. Okay, refractive indices of the two media, N1 and N2. And you can see the basic definition of that one. And we can modify this particular equation like beta 1 sin theta I is equal to beta 2 sin theta T. So in further lectures we are going to use this particular relation. Okay, so how did we get this one? First of all, you see what is this N1, refractive index of the wave in medium 1. That is actually the ratio between the light velocity, okay, and the velocity of the wave in the medium. So C by some V1 we have to write, and here C by some V2 because medium 2. And you can able to substitute the velocity formula, then it can be rewritten like phase constant beta 1 and here also phase constant beta 2. So that we can able to utilize this one also as the Snell's law of refraction. Okay, so Snell's law contains two things. One is theta is equal to theta R and second one is this one. Okay, now coming to what is this perpendicular polarization definition. So as I said previously, the electric field orientation, it depends on the name of this particular polarization is given with respect to electric field orientation. Okay, so how the electric field orientation is available means you have to take like this. Okay, how? This is the electric field, this is the direction of wave, and this is the magnetic field. So these three must be perpendicular to each other, and this electric field should be perpendicular to the plane of incidence. Previously I told that this is a screen. Now exact definition is, what is the plane of incidence here? that is XZ plane. Already I have given that one. What is plane of incidence? The plane which contains normal to the interface and the incident wave. That means normal, incident wave. That means this plane is the plane of incidence, that is XZ plane in our case now. So if I take like this, thumb is always in the direction of wave and this forefinger is coming out of the board, coming out of the XZ plane. That means it is perpendicular to the plane of incidence. Since electric field is perpendicular to the plane of incidence, we can tell it is the perpendicular polarization. So how to indicate this one? We have to take like this, na? Dot circle represents that particular electric field is coming out of the board. Okay, so here electric field, since it is for the incident wave, we have to take EI. And wave is traveling in this particular direction, so arrow mark I am giving like this, and magnetic field is coming like this, na? So or we can able to represent like this also. Thumb is always in the direction of propagation, and if you close these four fingers like this, from the electric field to magnetic field we have to close. So electric field is coming out of the plane of incidence, so that magnetic field should be coming and closing like this. Okay, so that we can able to tell this is the HI. So HI will be like this. Okay, so HI is there on the plane of incidence only, but EI is coming out of the plane of incidence. So since the electric field is perpendicular to the plane of incidence, it is called perpendicular polarization. That is the exact definition of the perpendicular polarization. Okay, now this perpendicular polarization can also be called as S polarization. Okay, what is S polarization means? Senkrecht. Okay, what is this one? It is actually German word. Okay, the meaning of this one is perpendicular only, and from this particular word they have taken S, and that is why it is called S polarization. Next one is horizontal polarization, or this can also be called as E polarization. See carefully, this perpendicular polarization name was given with respect to electric field orientation only, but that is we have compared with, we have taken with respect to plane of incidence. This one we have taken with respect to, this name was taken with respect to plane of incidence. Since electric field is perpendicular to the plane of incidence, that is called perpendicular polarization. You see, this is the electric field coming out of the plane of incidence. How the boundary is there, how the interface is there, like this. But for this interface, how this electric field is there? Parallel. Okay, that's why this is called horizontal polarization. Okay, why it is horizontal polarization? Means electric field is horizontal to the interface, so that it is called this horizontal polarization or E polarization, because of the same reason. Electric field, how the electric field is oriented with respect to boundary, how the electric field is oriented with respect to interface, based on that one these two names are given. Okay, everything is with respect to electric field only, but how this electric field is oriented with respect to plane of incidence, accordingly this perpendicular polarization name was given. How this electric field is oriented with respect to interface or the boundary, with respect to that point, these two names are given. And already I have told about the how S polarization name was given. Okay, this is just basics of this one. Now we will see exact orientations of this incident wave. Already I have given here. Reflected wave, how it will be represented, and transmitted wave, how it will be represented. These things we will see one by one. So here also same thing we have to take, na? This is x-axis, y-axis is coming out of the screen, so that xy plane is the interface, z is the normal to the interface. So as I said, we have to take this incident electric field, okay, that is incident on this boundary, and since we are working with the perpendicular polarization, the electric field must be coming out of the plane of incidence. So EI is coming out of the plane of incidence, that is XZ plane is the plane of incidence. Next, this magnetic field of the incident wave HI is represented like this. This is the orientation of the HI. Electric field is coming out, and this is the wave representation, and this wave vector is making the angle theta I with the normal. Okay, now we will talk about the reflected wave. Okay, so because of the impedance mismatch, some power will be reflected back, that is also in the form of the electromagnetic wave only, so that is reflected back. We have taken like this. Okay, you see, how we have given the orientation of electric field and magnetic field, thumb is direction of propagation. Then if you close your 4 fingers like this, this 4 fingers should be from E to H. E to H, like this also we can take. Instead of taking like this, you can take like this also. So same thing will follow here also. So anyhow, we are working with the perpendicular polarization. So electric field must be perpendicular only here also. So reflected electric field is coming out of the screen. Now we have 2 things are over. One is electric field orientation coming out of the screen, and second one is direction of propagation, that is also indicated. Remaining point is only magnetic field orientation. How it will be represented? Using this law only. So thumb is representing the direction of propagation. So electric field is like this, thumb is like this, electric field is like this. So we have to close like this. That means this is the representation of reflected magnetic field. Okay, that will be represented like that. And once if you complete the incident electric field orientation, the transmitted electric field orientation is very simple. That means the representation of the entire transmitted wave is simple. That is similar to this one only. So, and here before going to that one, what is the angle made by this one? Theta r actually, but according to Snell's law of reflection, theta r is equal to theta I. So for your convenience, here I will represent that one. Theta r is equal to theta I. So that here you can able to write actually theta I also. There is no problem. Next, the wave will be refracted, so that this angle will be different, that is theta t. This is the refracted wave or the transmitted wave in the medium 2. Okay, and since it is a perpendicular polarization, electric field should be coming out of the plane of incidence ET. And how this particular wave is indicated, magnetic field is indicated in a similar manner. Here also HT will be available, or you can check like this. Okay, this is the direction of propagation, electric field, this is the magnetic field. Closing, we are closing from the electric field to magnetic field. Thumb should represent the direction of propagation. This is the way of representing the perpendicular polarizations. Okay, then now what we need to do? Okay, we have sent the electromagnetic wave from medium 1 to medium 2. Since these two are having 2 different impedances, what has happened? Some power will be reflected back, some power will be transmitted. So whatever the total power you have incident here, out of that one something is reflected back into the same medium, and remaining thing will be transmitted into the other medium. This is what is happened. Now what we need to do means, how much is reflected, how much is transmitted, that is what we need to find. Okay, so what we are going to see in the remaining lecture is nothing but how much power is reflected back into the same medium, how much power is transmitted into the second medium 2. That is what we need to see with the help of 2 things. One is this transmission coefficient and reflection coefficient. Reflection coefficient is given by gamma. Since we are working with perpendicular polarization, this is the symbol was given, perpendicular symbol. So gamma perpendicular refers to reflection coefficient in perpendicular polarization, and tau perpendicular, that means a transmission coefficient in perpendicular polarization. Same thing we will see in case of the parallel polarization also. Okay, now we need to get these 2. So before going to see the expressions here, I will tell how to calculate this gamma perpendicular. So gamma means what? Reflection coefficient in terms of the electric fields we will find here. So that is reflected electric field ER by incident electric field, that is EI. So EI is available here, ER is available here. In between these 2 we have to take the ratio, that is gamma perpendicular. Similarly, tau perpendicular is the ratio between transmitted electric field and incident electric field. So here transmitted electric field is there. So if you take the ratio between these 2, you will get a tau perpendicular. These are the things we need to get. That is our plan to get to do what we have to do in this particular lecture. Okay, so now we are going to write expressions for the electric fields and magnetic fields here actually. Okay, so one thing you observe, electric field is coming out of the screen, electric field is coming out of the screen here also, and electric field is coming out of the screen. Here we have to apply the boundary conditions. Okay, so boundary conditions of this particular medium, okay, which is the medium 1, medium 2. In between these 2 boundary is there. So boundary conditions means on the boundary, okay, how the tangential components of the electric fields are related, or the normal components of the electric fields are related. or because it is related to magnetic fields also, how the tangential components of the H field and how the normal components of the H fields are related. Those things we have to take. So anyhow, for this particular concept, we need only tangential components only. So what is the tangential components nature here? ET1, it is not this transmitted wave. So in order to avoid the confusion, I will take E tan 1, that is equal to E tan 2. Then H tan 1 is equal to H tan 2. H tan 2, like this we can take. Okay. So tangential components in the medium 1, this 1 refers to medium 1. Tangential component in medium 2. Tangential component of the H field in medium 1 is equal to tangential component of H field in medium 2. But if you observe the tangential components in the medium 1, it is related to two waves. It is incident electromagnetic wave, here reflected electromagnetic wave. Both are there in the medium 1 only. And here transmitted electromagnetic wave is the only wave available in medium 2. Accordingly, we have to write the equations carefully. Okay. So now you see, electric field is oriented perpendicular to the plane of incidence. So it is already tangential to the plane. This is the plane. Okay, this is a boundary or the interface. Electric field is available like this. So it is already tangential. Electric field in case of the reflected wave is also tangential. Electric field in case of the transmitted wave is also tangential. So simply here we can write, since two electromagnetic waves are there in the medium 1, it is given by EI plus ER. It is equal to ET. Why did I write like this? These two are the tangential components available in the medium 1. Okay, one is EI is related to the incident wave, ER is related to reflected wave, and only one wave is there in the medium 2, that is transmitted wave. Its a corresponding tangential component simply I have represented with ET. EI is the tangential components of the incident wave, ER is the tangential component of the reflected wave. For the time being I have taken like that. Now same relation we have to write in for the this particular H fields also. Okay, so how to write that one? H field is not directly oriented, not directly tangential to the field, tangential to the interface. Interface is like this, but H field is like this. So what we need to do? We have to resolve this vector into parallel and perpendicular components. Okay, and we need to take tangential component only, or we can take the terminology like tangential component and normal component. So anyhow, normal component is not required to us, only tangential components are required to us. So we have to resolve this particular vector into two vectors. One is, this is the tangential only, this interface is like this, this is the tangential component. If you take like this, that is a normal component. Anyhow, normal component is not required to us. So this is theta I angle will be there. So this particular vector we need. How to get that one? This is HI. So this is given by adjacent. Okay, adjacent side only. So this is given by HI cos theta I. By using cosine function only we can get adjacent side. Similarly, this one also. This HR also not adjacent to the interface directly. Okay, this is like this. So what we need to do? We need to resolve this one. So we have to take this adjacent component like that. Okay, tangential component of the HR is this one. And the angle here is theta I. Again that is adjacent side only. So that we can take here HR cos theta I only. We can use I because theta R is equal to theta I. But here one thing you need to remember, that is this tangential component is representing downside, this is representing upside. So both are opposite in direction. So I will take here minus symbol. Okay. So it is equal to, these are the two tangential components of the H field in medium 1 over. Next, according to this condition, here tangential component of this H field we have to take. Again we have to resolve this one like this. So what we will get here? HT cos theta T, like this we can take. Okay. So in this manner we can apply, just we have applied boundary conditions related to electric fields and magnetic fields. Now by using the relations like this, ER by HR, or it is equal to something, and EI by HI, it is related to something, and ET by HT, it is related to something. These are actually giving the impedances, okay, because voltage by current or electric field by magnetic field is given by its impedance. But these two are related to medium 1. So these two are given by eta 1, and this is related to medium 2. So it is given by eta 2. Okay. So using these relations, now we need to get, our motto is what? To get the ratio between ER and EI, the ratio between ET and EA. That means reflection coefficient we need to get and transmission coefficient we need to get. For that purpose, here if you want to get this one, we have to eliminate ET. Okay, we have to eliminate ET. And in order to get this one, we have to eliminate ER. Like that we have to proceed. Okay. So for that particular purpose, I am going to the next slide. So once again I am writing the whatever the equations we need, those equations I am writing here. Those are EI, ER, this is ET, and second equation we got HI cos theta I minus HR cos theta I is equal to HT cos theta T. This is what we have. Okay. Now I will try to get this reflection coefficient gamma perpendicular. For this particular purpose, what I need? Ratio between ER and EI. So that I need to eliminate ET. And before going to that, I will express this entire equation in terms of the electric fields only. So what will happen? E by H is equal to eta. Accordingly, this HI can be written as EI by eta 1 cos theta I minus this is ER by eta 1 cos theta I. It is equal to ET by eta 2. This is cos theta T. Like this we have written. Now using these two equations, you take this is equation 1, equation 2. Using these two equations, what we can do? We can get the ratio of ER and EI, or we can get the ratio of ET and EI. So to get this reflection coefficient, we need to eliminate ET. Okay. So in this equation, wherever ET is there, you substitute equation 1. That means EI plus ER. So what we'll get? EI by eta 1 cos theta I minus ER by E theta 1 cos theta I is equal to, here what we can write? ET means EI plus ER by eta 2, that is multiplied with cos theta T. Now we can write all the EI terms at one place, all ER terms at one place. So, and by taking EI is common, here what we have? Cos theta I by eta 1. Here EI term is there. By sending this side, minus will get, and cos theta T by eta 2. Like this will get. And it is equal to, here ER term is there, ER times of cos theta T by eta 2. And here also ER term is there, send that one this side. So what will get? Here minus is there. By sending to right side, it will be plus cos theta I by eta 1. Like this we can write. Okay. LCM will be eta 1, eta 2. LCM will be eta 1, eta 2. Both will be cancelled. So we can write ER by EI is equal to. Okay. That means this EI we have sent here. So what is the numerator we will get here? Eta 2 cos theta I minus eta 1 cos theta T by, here what we get? That is eta 2 cos theta I plus eta 1 cos theta T. So actually we have defined this ER by EI as a reflection coefficient. So gamma, but we have defined this one in case of the perpendicular polarization, that's why gamma perpendicular. So this is the reflection coefficient we got. You need to remember this equation. Okay. And here I will give this one quickly. These directions we will take like this. Okay. This is the incident wave, reflected wave, this is the transmitted wave. And the incident wave is making the angle theta I, this is making the angle theta I or theta R, and this is making the angle theta T with the normals. Okay. This is actually oblique incidence where we have taken perpendicular polarization. Okay. So if I want to make this is normal incidence, what we need to do? Normal incidence means what? This is a normal to the interface. Normal incidence means the electromagnetic wave should be parallel to the normal. This is actually normal incidence. NI, normal incidence. This is oblique incidence, OA. So the incident wave is making certain angle. It is making certain angle with the normal to the interface. That is called oblique incidence. Instead of this one, if the incident wave is not making any angle with the normal to the interface, okay, then here we can tell theta is equal to 0. Then automatically this reflected wave is also not making any angle with the normal to the interface. This transmitted wave is also not making any angle with the normal to the interface. So theta is 0, theta r 0, theta t 0. So just we will check this one. In this case, what is gamma? Already we know. That is eta 2 minus eta 1 by eta 2 plus eta 1. This one already we know. Now we will check this one. Just by taking this theta I, theta r, theta t. Because the availability of the non-zero values of theta I, theta r, theta t, we got this equation now. In case of the perpendicular polarization, we got the reflection coefficient is equal to eta 2 cos theta I minus eta 1 cos theta t by eta 2 cos theta I plus eta 1 cos theta t. This is what we got. Now just we will check whether it will be correct or not just by taking theta I 0, theta r 0, theta t 0. So cos 0 1, cos 0 1, cos 0 1, cos 0 1. So it leads to this formula only, na? Eta 2 minus eta 1 by eta 2 plus eta 1. So it is valid. Okay. So this is the equation you need to remember, and this is the just the reflection coefficient only. Next we are going to see the transmission coefficient also. Okay. That is what we are going to see now. So for the explanation purpose, I will take the equations again. So EI plus ER is equal to ET, and then HI cos theta I minus HR cos theta I is equal to HT cos theta T. Okay. So again I will modify this one, that is EI by eta 1 cos theta I minus ER by eta 1 cos theta I is equal to ET by, this is eta 2, because it is related to medium 2, I have to take here eta 2. This is cos theta T. Now we are going to get transmission coefficient, okay, of perpendicular polarization. So what is the transmission coefficient in this case? ET by EI. That means we don't want here ER term. So replace ER term from this equation. So now you take again previous equation only 1 and this is 2. So using 1 we have to replace this ER to get the ratio just ET and EI. So what we need to do? Just I am modifying that one. So EI by eta 1 cos theta I minus this ER is nothing but from this what we can write ET minus EI. So ET minus EI by eta 1 cos theta I is equal to ET by eta 2 cos theta T. Like this we can write. Now again same thing, we need to get the ratio ET and EI. Accordingly we can able to arrange. So I am writing all the EI terms at one place. Now you see EI by eta 1 cos theta I minus into minus is plus EI by eta 1 into cos theta I. So two terms, same terms. That means 2 EI by eta 1 cos theta I. It is equal to, I am sending this ET term this side. So and I am taking ET is common also. So what can I get here? Cos theta T by eta 2, and this is minus by sending this side plus. So ET we have taken common, and here we will get cos theta I by eta 1. Here eta 1 is there, but here LCM is eta 1 eta 2. So eta 1 will be cancelled, in the denominator eta 2 will be there, that you can send this side. Okay. So what we will get here? I am getting the ratio, that is ET by EI, that is equal to 2 is there. Eta 1 anyway have cancelled. Eta 2 is coming here. 2 times of eta 2 times of cos theta I. And here what we will get? By, this is eta 2 cos theta I plus eta 1 cos theta T. This is what we got. Okay. So this is the ratio between transmitted electric field and the incident electric field, so that according to the definition we can able to tell it is a transmission coefficient for the perpendicular polarization. So this is what we got. So reflection coefficient equation we got, and transmission coefficient equation also we got. And again you can able to check according to this normal incidence case. If you take theta is 0 and theta t is 0, it leads to 2 times of eta 2, 2 eta 2 by eta 2 plus eta 1. That is what you will get. Okay, so we have got that one, and for the explanation purpose we can take like this also. Okay, so this is the thing we can able to tell. So those two equations I am writing at one place now, whatever we got. So that is first I will take this incident wave, transmitted wave, reflected wave, and here I am taking gamma perpendicular. What we got, that is equal to eta 2 cos theta I minus eta 1 cos theta t by eta 2 cos theta I plus eta 1 cos theta t. This is what we got. This is the reflection coefficient. Now the transmission coefficient tau perpendicular is equal to 2 times of eta 2 cos theta I by denominator is same thing, that is eta 2 cos theta I plus eta 1 cos theta t. For the normal incidence, we got the relation between reflection coefficient and transmission coefficient. What is the relation? 1 plus gamma is equal to tau. 1 plus gamma is equal to tau. This is the relation we got in case of the normal incidence, and same relation is followed here also. Just you can check 1 plus gamma perpendicular. So just you take plus 1 here, then this by taking LCM, this numerator will be here. That means this denominator is added with the numerator, where this eta 1 cos theta t will be cancelled. So this one will come 2 times. That means it is equal to 2 times of eta 2 cos theta t, cos theta I, by same denominator will be there na, eta 2 cos theta I plus eta 1 cos theta t, but it is exactly equal to tau perpendicular only. You can check that one. Okay, so the relation 1 plus gamma perpendicular is equal to, we can able to write tau perpendicular. This is what we can tell. Okay, so the same type of relation we have seen in the normal incidence, now it is for oblique incidence in that perpendicular polarization. Okay, here only I will tell one thing, the same relation is not valid in case of the parallel polarization. Okay, we are going to see that one in the next class. Okay, and we will talk something regarding this particular thing. So if you observe one thing, we have incident one electromagnetic wave. Out of that one only something is reflected back, and remaining part is transmitted. That means whatever we have sent, that is splitted into 2 things. One is reflected, second one is the transmitted. Okay, then incident must be more compared to this electric reflected thing and transmitted thing. But here what is happening? We are observing that this transmission coefficient is more than 1. How it is possible? Same thing I have discussed in case of the normal incidence also. How it is possible means, it is just giving the relationships according to electric fields. But law of conservation of power is valid, so that there is a change in case of the magnetic fields. Total thing we have to consider na. So here we know about the Poynting theorem. Power will come from the cross product of electric field and magnetic field. So law of conservation of power is valid here also. So don't confuse by seeing this particular equation. Don't think that this transmitted electromagnetic wave power is larger compared to this incident electromagnetic wave. Don't see like that. It is not about power. It is just about electric fields only. Okay. So always law of conservation of power is valid. That is what you need to remember. Thank you.